Okay, Galileo, right. The Leaning Tower, dropping stuff. We all know that image.
Yeah.
It's like the picture of science.
It is. It's iconic.
But I bet there's more to the story than most people realize.
Oh, absolutely. Way more.
And that's what we're doing today. A deep dive.
Love it.
Going past the Galileo story to see what else is going on.
Because it's never just one guy, right?
Never. So you found some sources about, I gotta say, this blew my mind.
Uh-oh, what'd I do now?
People were questioning gravity, like way before Galileo.
Oh, yeah. It goes way back. Like 6th century.
6th century. Seriously.
Yeah, there's this guy, John Philoponus, scholar.
Okay.
And he's already saying, wait, Aristotle might have this whole heavy falls faster thing wrong.
Hold on. We're talking 1,500 years ago, almost.
Give or take.
And they're debating this stuff. It's like, how much cool science are we missing from history?
Right. It makes you think. And then it's not just him. We've got mentions of like Italian guys actually doing experiments. Oh, later. More like the 1500s. But still. Point is, this idea was bouncing around.
Fascinating. So they're testing this out. Like actually dropping stuff.
Seems so, though the details are a bit thin on the ground there.
Ah, the mysteries of history.
Yeah.
So, okay, 16th century, what's happening then?
Well, now we're getting names we might recognize. Domingo de Soto, Giambattista Benedetti.
Okay, I've heard of Benedetti vaguely.
Yeah, he was thinking about, like, if you drop iron and wood...
Which falls faster.
Exactly. Basic question, huge implication.
Right. It's not just the speed, it's the why that matters.
And that's what's so cool here. They're chipping away at Aristotle's ideas.
Laying the groundwork.
Precisely. And this is where we get to something really interesting. The Delft Tower experiment.
Delft Tower.
Yeah, in the Netherlands. 1586. Simon Stevin and Jan Cornets de Groot.
Okay.
They dropped these lead balls, different weights.
Off the tower.
Off the tower, same time. They hit the ground at the same time.
So before Galileo even.
Decades before. And it's all there in Stephen's book, The Principles of Statics.
But we always hear about Galileo and the Leaning Tower. Why is that?
Well, the Leaning Tower is, leaning.
Yeah.
It's a good visual.
True, it's hard to beat that image.
Plus, those stories about Galileo came later from his student's biography.
Uh-huh. So maybe not as accurate.
Most historians think the Leaning Tower thing was more like a thought experiment or a demo for students.
Okay, so it might have happened, but the point is, Galileo was already onto this idea.
Exactly. The falling objects thing was part of a bigger picture he was building.
So even if he did the tower drop, it was to show what he already knew.
Right. He was already challenging Aristotle in some pretty fundamental ways.
Like what?
Well, at first he was saying, look, if you have two things made of the same stuff, they'll fall at the same speed.
Makes sense.
But that already contradicts Aristotle.
Ah.
Then he goes even further. The famous thought experiment.
As I've heard of. Tying the rocks together, right?
That's the one. You tie a heavy rock and a light rock together. Now, if Aristotle's right, this combo should fall slower than just the heavy rock alone because you're adding the light one's slowness.
Right, dragging it down.
But then he's like, wait a minute. The combo is also heavier than just the heavy rock, so it should fall faster. It's a paradox.
So he basically used logic to poke holes in Aristotle's theory.
Brilliantly. And that led him to the idea that it's not about the weight itself, it's about how they accelerate.
Acceleration is the constant.
A bingo. Which, revolutionizes how we understand gravity.
And that's just the beginning. We'll pick up this thread next time because this leads to all sorts of amazing stuff.
Oh yeah, buckle up. We're going to the moon and beyond.
So we're back, and we've been talking about how Galileo really shifted our thinking about gravity.
Yeah, big time.
But it's not like science just stops there.
Oh, no. It keeps going.
And one of the coolest things I remember is years later, the Apollo 15 mission,
Ah, yes.
astronaut David Scott, dropping the feather and the hammer on the moon. I saw that as a kid. It just blew my mind.
It's such a perfect visual, right? Like, here's proof.
Total proof. No air resistance, totally different masses, falling at the same rate.
Exactly. It really drives home that Galileo was onto something fundamental.
You mentioned something called the weak equivalence principle before the break.
Right.
Could you maybe explain that a bit more in like simple terms?
Sure. Basically, it says that inertial mass and gravitational mass are the same thing.
Two kinds of mass.
Well, kind of. Think of it like this. You push a shopping cart.
Okay.
The harder you push, the faster it goes, right? That's because of its inertial mass, how much it resists being moved.
Inertia, yeah, I get that.
Now, same cart, but just sitting on Earth. Earth is pulling on it with gravity, right? How strong that pull is depends on the cart's gravitational mass.
So one's about motion, the other's about gravity.
Exactly. But here's the wild part. As far as we can tell, those two masses are identical.
Wait, so the thing that makes the cart hard to push is also what makes Earth pull on it.
Pretty much, it's this one property that does both those things.
That is wild.
And that's the weak equivalence principle. And that idea, simple as it sounds, has huge implications.
Like what?
Like it's a cornerstone of Einstein's theories of relativity.
Oh, here we go, Einstein.
Had to come up eventually. But see, Einstein loved this equivalence principle.
He saw something in it.
He did. It wasn't just a quirk about gravity, it was a clue to how space and time actually work.
I remember reading about his thought experiment with the elevator, right?
Yeah. The guy in the elevator can't see outside. Is he feeling gravity or is the elevator just accelerating upwards? He can't tell.
Mind-blowing stuff.
And that led Einstein to this idea that gravity and acceleration are, in a way, the same thing,
Whoa.
which became a big part of his theory of general relativity.
So we've gone from Galileo dropping stuff to this whole new view of the universe.
Pretty neat, huh? And what's even cooler is scientists today are still testing this equivalence principle.
Really? Why? I mean, we're pretty sure about it by now, aren't we?
We are, but there's always room to learn more. Plus, our current theories about gravity, they don't explain everything.
There are still mysteries.
Oh, yeah. Like dark matter, dark energy, huge chunks of the universe we can't even see directly.
Right, the invisible stuff.
And some physicists think that maybe, just maybe, tiny violations of the equivalence principle could be a clue to what dark matter and energy actually are.
So by looking for these tiny cracks in the theory,
We might find a whole new understanding of the universe.
that is so cool.
And that's what those ultra-precise experiments are all about. Pushing the limits of measurement to see if anything breaks.
Like the more we learn, the more we realize we don't know.
Exactly. And that's what makes science so exciting. There's always more to discover.
It's wild to think all this, it comes down to how gravity works.
Yeah, it's fundamental, isn't it?
And you said there are these experiments trying to find even tiny differences in how gravity acts.
Right, super precise measurements.
Why bother, though? I mean, isn't general relativity like the theory of gravity?
It's our best one so far, that's for sure.
So why keep pushing?
Because it's not the whole story. There are things general relativity doesn't explain.
Oh, like what?
Well, the big ones are dark matter and dark energy. We know they're out there.
Because of how gravity acts, right?
Exactly. We see their gravitational effects on galaxies, on the whole universe.
But we can't see them.
Not directly, no. It's a puzzle.
And some scientists think this might be related to the equivalence principle.
Some do. The idea is maybe different kinds of stuff, different matter or energy, experience gravity slightly differently.
So the equivalence principle, as we know it, might be wrong.
Not wrong, maybe, but incomplete.
Uh-huh. So these super precise experiments.
They're trying to find those tiny differences. If they exist, it'd shake things up big time.
Earlier you mentioned torsion balances.
Yeah. Imagine like a tiny dumbbell.
Okay.
Two different materials on this incredibly sensitive, thin fiber. Any gravity difference, it'll twist the dumbbell.
They can measure that twist.
Yeah, that's the whole point. They're measuring these incredibly small movements.
Looking for anything out of the ordinary.
Exactly. And if they do find something, wow, that would mean our current gravity theories are missing something big.
Like rewriting the textbooks big.
Potentially. It'd mean there's a deeper level to gravity that we haven't even grasped yet.
So, starting with Galileo, just dropping things, centuries later, we're still following that thread.
It's a pretty amazing journey, right?
This whole deep dive has been incredible.
I'm glad you enjoyed it.
We've gone from ancient philosophers to Galileo's experiments to Einstein, and it's clear there's always more to learn.
That's the beauty of it, isn't it? The universe is full of mysteries.
And I think that's a perfect place to leave it. This idea that even when we think we know something, there might be a whole other layer underneath.
That's a great takeaway. Never stop questioning, never stop exploring.
Absolutely. Thanks for joining us on this deep dive into gravity. Until next time, keep looking up.